Okay, so today I took a paper whose title is Radiomics Guided Vision Transformers for Survival Analysis. Whenever I pick up a paper, I focus that what came into the mind of the author, how they're researching on these algorithms or techniques, what is their post, what is their perspective. So that research paper I will share, I already did in the group. You are available with. If you can, you please open that. Vision transformer, not a new name for you all. I guess we already covered the entire algorithm for classification, segmentation. All right. First, machine learning techniques or algorithms we have covered for classification. In this machine learning, I'm not talking about simple logistic regression or decision tree to classify. I am talking about the feature, how you extract from the images. Like you already know from my sessions that the techniques like CLHAE, contrast limited histogram equalization, in order to improve the pixel intensities which are present at the border areas. Then GLCM, gray level co-occurrence matrix, that the pixels which are coming together, if we rotate or any transformation, if we apply on them, do they come together again, applying all these activities. So GLCM. There are many other statistical techniques which we have studied in our previous sessions. Okay, so this is what happens prior to convolution neural network, where we apply statistical, this mathematical foundations step by step to extract the features, the relationship. Actually, not I will say fully relationship between the pixels. No, it's like statistical analysis, statistical analysis over the images. Okay, that means the distribution of pixels. Ultimately, you can say distribution of pixels. Okay, fine. This is what we follow. Then, after convolution neural network, things changed, and we started applying kernel or filter based convolution. Okay, we do have a filter matrix that runs over an image and create a feature map. This is what we do. We are having an image, we apply kernel or a filter, we get a feature map. Okay, and along with this convolutions, we do have a pooling layer, min pooling, max pooling, average pooling, global average pooling, where we organize these layers with the convolution. You've seen pre-trained models came after, like with this convolution, pre-trained models came. VGG till we have covered all with the architectures I explained. VGG 16, 19, inception, exception, dense net, resonate, efficient net, mobile net, everything you have learned. And this convolution based technique for feature extraction to get good information from the data, then give it to the neural network for training. Because here we are expecting relationship between the pixels, we are not only expecting the statistical distribution of pixels. So statistics is much more related to a kind of a data where we organize it into tabular format, where we check outlier, etc., etc. That is the basics of machine learning and data analysis. So we apply statistics there more. But in image data, this is unstructured in nature. So when the data is unstructured in nature, we do have a different approach to gain features from the image. Okay, doesn't matter that you can't train a neural network with the image directly. You can do that. Image, neural network, you can do that. But this is unnecessary training a model with huge amount of data because not everything present in image is important. So better you apply convolution over the image, then give it to the neural network for training. So in convolution, pooling such kind of layer organized you have seen, and then the neural network we do have dense layer, dropout layer, all such kind of layers present with us. Activation functions, okay, sigmoid for binary, then sort max for multi classification, okay, and we get so and so results. So for short term dependencies, this convolution was good, and then we proceeded ahead with the transformer. You very well know about these transformers. Okay, dividing image into patches, then applying encoding, that means numbering of the patches. You can do embedding, converting the patches into vectors, and then applying attention mechanism. This is what you need to do. Okay, that's the main game which happens after the attention mechanism. Then later on, you can have your neurons for training, neural network for training. That is what you can do. So here we expect a long term dependencies between the patches. Okay. An inspiration from text based transformer architecture converted for image based. Okay, classification task. Swing transformer, max transformer, those also covered. At some places, we have done hybrid also, hybrid architecture. That is CNN, convolution, and VIT both are merged because this VIT takes computational cost high. CNN are not that much. VIT is computationally costly. So right now we are expecting that make an architecture, make a model that takes less time to or less memory, less space, less resources to perform your tasks. Okay, I think in the previous sessions, previous lectures, I also taught about image generation. Okay, I talk about image generation where Jans discussed. Then variational autoencoder discussed, autoencoders discussed, diffusion model also I discussed. Okay, diffusion model discussed. Fine. And some experimentation we did because why? Right now the people are like classification not a big deal because right now you are having LLMs, intern, AI agent, LLM, because you are available with the brain. LLM is a brain. It's a language model, it's a brain. And you have made a so powerful brain. So once you are available with so powerful brain, and now what you are doing is you can enter into any of the system and scan that particular system. Okay, to get the result. That's what you are doing right now by using this brain. Okay, like I told in the previous session also that Anthropic, this Claude one, they have released one model, or I think they are working on this particular AI, Mythos. I think that's the name for cyber security, and it has found the errors in operating system and other websites which is difficult to be found by a human. That means it can scan the entire software or websites. So now it like there is a challenge for financial websites, like it will take few days, it will take only few days to get it into any of the website, like all this banking and all. It can go inside these because this software, this AI knows the entire framework, entire architecture. Okay, and how to, because this is made to identify cyber limitations. Okay, so therefore it is having a well knowledge of the web, like server side scripting and client side scripting. It knows everything. That is why it can find the errors. So very strong model. Governments are concerned with this model. They reached a very high limit of AI. And right now, okay, one more thing. Just recently, ChatGPT also released one model for image generation. Now it's not. It's for us not a challenge to make some image for our research paper also. Not a challenge. It will create clean, refined image for your research architecture on the basis of prompt, on the basis of algorithm, on the basis of technique. You just tell that kindly make an architecture for us. The Chat GPT will make image generation so high quality. Okay, so image can be generated, a text can be generated, all other events can be accessed by AI. There are so many layoffs. Every company are in a layoff, giving layoffs. 8,000, 11,000. Okay, such kind of employees because they want to invest in AI resources. AI resources. Okay, they want computing elements. They want obviously the research people who can build some novel algorithm technique, and on the basis of these resources, that's what they want to purchase, like data centers and etc. etc. Okay, they are having the ideas with the help of research people. They know algorithms. They are having a lot of data available with them. Okay, with these data centers, they will train, they will test, and definitely they will deploy or release the model. Rather than paying to someone, what the sense of paying to someone? Everything is being prepared. Yeah. Okay, next coming years, you will see all these auto lectures and like many things, copy checking also, exam copy checking. Because why to pay to the humans if AI can check the copy? This is also happening. It's under trial process, I guess. In India also, this is happening. Copy checking, AI will do. Okay, there are a lot of bundles of copies are there. Let's give it to the scanner AI, and it will give in minutes your results. Why to invest this much of time in checking the copy also? All right, so machines are like so many activities which humans are doing. They are trying to slowly, they are getting into it. Previously, the kind of techniques which we do learn is for development via humans, by humans. For example, we do have a very good IT, India. Okay, so we are the people who are the developers. We are the good developers. Doesn't matter. We take all the software and etc. etc. Mostly from the US side, but we are good developers. in algorithm, in this data structures. Still now the people are much and more into data structure algorithm, and I was keep on hinting, now kindly switch yourself please. But campus selection and all these, they are into, okay, data structure algorithm, and no, it's over. Okay, so development part, we were, so whatever be the things we have done, we are the humans who are developing that now. And I think I told previously also, this is AI. Now machine itself is developing. There is a change. This I told, I think previously also, it's a different skill you need to understand. Whether machine is not a new thing which came into the world. Okay, for example, if we are having a calculator, we need to operate the calculator, we need to do the calculation. So far we were doing, we are the people who are running the machines, we are the people who are driving a car. Okay, car build, previously there was a bullock cart, and now there is a car, but who's driving the car? Human. And traveling from here and there, there is a getting scope of many, like employment because of this communication resource. This is different. You are not driving force, your machine is a driving force because of its intelligence. So you are removed from the loop. Understand this? It's a different kind of skill. So if you think that, okay, AI came and no, it's impacting a lot. It's it's impacting a lot. It doesn't, if it's not been visible, see, it's impacting a lot. Our IT services also, and other sectors also. It's impacting. Okay, fine. Now, what is there for our paper today? Let me share the entire screen. Here is our paper. Now, how to survive in this particular impact of AI research? That's the only thing which will help in survive. Praveen sir, is everything fine, sir? I haven't talked to you, so, sir, from long time. Okay. You're listening to me, sir? Right now, Praveen sir is on mute. Maybe he will reply later on. Anyways, here is the paper. Radiomics guided vision transformer for survival analysis. What is there in the paper? Vision transformers have shown strong empirical performance on high dimensional medical image data, yet the behavior, understands survival objectives, and interpretability of their attention mechanism remains poorly understood. Okay, okay. They are telling right. Vision transformer we have applied in so many problem statement, either a brain tumor, either breast cancer, either chest x-ray, etc. A transformer we have applied, and every time we are getting 90-95% plus accuracy. That is no doubt about the transformers, we are getting good scores. But they are saying something different. The authors told, yet the behavior under survival objective is not clear, and the interpretability of the attention mechanism is also not understood. Okay, attention mechanism in transformer we are aware that is q dot k ka transpose square root of d max dot v. So we know about attention formula, we know about it. But author told that, first of all, with transformer, you are not able to tell the survival rate. No, nothing talked about survival thing. Also, this attention score which we use in the transformer, that is not interpretably or been clear, that we came into a conclusion that this is going to happen ahead or something. We just only using such a such mechanism, such formula for classification task. Simple. So that's what author thought behavior of survival and interpretability of attention remainly poor in nature, difficult to understood. And under shallow VIT, we design control experimentation showing the token level attention dynamics to recover outcome related relevant region, and that attention based threshold holding enables effective token pruning, improving both interpretability and predictive performance. So, authors told that we did some experiment. What kind of experiment we did? In a controlled system, token level attention dynamics, token level, obviously you know na, patch is token only for image. We divide the image into patch, so patch is token only. See, one more thing, what I understood right now after getting the reviews on my paper. So the author, sorry, the reviewers will ask you that are you doing your experiment on image level, are you doing your experiment on patient level, are you doing your experiment right now? Here, the author told token level. So, where actually your experimentation is happening, you need to clearly mention where you have divided your data. Sir, we have divided our data on patient level. We have divided our data on image level, or we are working on token level. You need to clearly mention how you divided, what made you to divide this thing, what will happen. Okay, you need to clear in your article. Okay, so in the abstract, the author told that we are doing token level attention, because obviously at tokens only, or the patch only, we apply the attention mechanism. We need to recover relevant regions. We need to recover relevant regions based on the attention to perform effective token pruning, because not every token is important, improving both interpretability and predictive performance. Okay, okay, okay. Well, image to patch or token to attention. All right, fine. So, like this is the image, we divide it into patch, and then we convert them into vectors, and then we apply attention mechanism, and based on the attention we train the model. And not every patch will get the high attention to attend to any other patch. Okay, so there will be some pruning also. They are saying pruning. Those patches who are not important for me to justify that this is malignant or this is benign. Okay, not justifiable. So just prune those patches, remove those patches. Okay, and only keep those patches which are important for us, which are having some information, which are having high attention, and look inside those patches. What made them to give such kind of attention? That's what the author told. That they told that at attention level, at token level, obviously based upon the attention, we are trying to improve interpretability and predictive performance of the model. That has been not shown previously. That means we haven't worked in depth. We were much more towards a result that okay, this is VIT, and apply this thing and getting high accuracy and done. But we are not into in depth. But right now, author is in depth. Author is telling that we need to prune the token, or we need to prune the patches which are not relevant for us, and we need to see what attention has been given to them. If any of the patch is having less attention, then why to keep those patches for training, because they are not at all contributing. And also those patches who are having good attention, why they are having good attention, what is present in it, let's check. So here the authors are going in depth. So we study pre-trained deep VIT for survival analysis and propose a radiomics guided hybrid model that integrates pixel-based embeddings and interpretable radiomic features through multimodal Cox framework and contrastive alignment. Right now, this thing, contrastive alignment, we are also used in our research paper. Contrastive alignment is getting highlighted. Many of the papers I have seen, we have also used in our research paper. Okay, so they are telling that we want to apply VIT for survival analysis. Along with, we are using radio mix guided hybrid model we are going to make based upon pixel based embeddings, not patch based, pixel based embedding with interpretable radiomic features. I'll let you know what these radiomics are. Through multimodal framework, Cox. I'll let you know what is this Cox and contrastive alignment. So this is what the authors are doing. Author did only one person, no, two-person is there. Shi and Lee. Okay, Chinese. That's the author did. In the research, applied to COVID-19 data set. Okay. And we'll see what happens. They are not talking about that we got 99% accuracy, 100%, nothing. Nothing. They are just only looking forward for clinically approval, clinically importance. The technique which we are applying, we are exploring VIT in detail. It's clinical interpretability we are looking forward for. We are not saying that this much accuracy, this much score, there is no comparison. We are only focusing deep in the VIT part. Okay, got it. So here is the abstract. In the introduction, okay, many things will be there. I have already made some notes for you that we can see. Radio mix is a quantitative approach in medical imaging that extract large number of handcrafted numerical features from images such as CT, MRI, PET or chest X-rays using advanced mathematical algorithm. What a human radiologist can see with the naked eye. So radiology, I guess. Radiomics, radiology, quantitative approach, not qualitative. Quantitative is a number. Quantitative is a number. So it's a numerical approach to extract handcrafted feature from the handcrafted or numerical features which are present, such as CT scan, MRI, PT, these. Okay, so the core idea is medical images consist of thousands and millions of pixels with a different intensity value. Radiomics convert these images into mineable high dimensional data by computing standardized features like shape, first order statistics like mean, median, entropy, skewness, kurtosis, and these things which I already told you. GLCM, CLHAE, GLRLM, and etc. etc. Gray level run length matrix runs on similar intensity, texture based, neighborhood. So you know how pixels are any high order feature present. So all statistical and mathematical techniques. That is radiomics. All right. So we apply first order statistics over the image to extract the numerical details from the image. That is what we call as radiomics. Okay, and it's a traditional technique actually. It's traditional technique. Right now we already gone far, like CNN, VIT. Okay, so it's a traditional technique. That's what they are saying. Okay, fine. All statistical, mostly in nature. Volume, surface area, shape, na shape like that. All these things are mentioned. So first we collect the image, pre-process the image, segmentation, region of interest, feature extraction using PyRadiomics mentioned in the paper. That is one of the library which we can apply. So whatever be the pixels intensity present in the images, we'll apply radiomics over it. Numerical representation of those. Okay, we'll remove the redundancy, noisy features, and use them in statistical models like Cox regression for machine learning for prediction. So ultimately, it's a basics of ML, the traditional techniques of ML. Okay, this is what the radio mix is. All right. Yes, yes, madam. Please.
Sir, if the data set is, sir, not having the balance,
Hmm.
unbalanced data
Hmm.
set,
Hmm.
by that time we will apply all the data augmentation techniques and
Ah,
everything.
yes, yes. Obviously, your data is not balanced, it doesn't matter. Pre-processing,
Whatever the
and pre-processing
whatever.
will be always be there, always be there.
Okay, suppose even though if I applied for the data argumentation,
Hmm, hmm,
still it is showing us the slight imbalance.
hmm.
By the time the model, it ultimately the model it will becomes the overfit. Maybe it may
Overfit.
reach to the
Okay,
99% or a something.
okay, okay. So,
By
madam,
the
now what
time,
we do? What
why
we do?
don't we apply the grid cam there? If it is over 15 model, can we apply the grid cam?
Okay, GradCam. So, madam,
Uh,
GradCam is a explainable AI technique to check that how a particular layer came as an outcome that this is a particular class. And
hmm.
mostly we pick up in the GradCam last layer, last convolution layer will pick up to see that which area it focused more. That is what happens in a GradCam. Let's gradient activation. Okay. So, ma'am,
Hmm.
the point is whether you overfitting in GradCam. Ma'am, GradCam is like explainable AI. So don't relate with the overfitting part. Why
Okay,
overfitting
okay.
happened? Why overfitting happened? The reason is okay. You're talking about imbalanced data, na? You're talking about
Yes,
imbalance.
for imbalanced data set, can we apply the grid cam? My question is.
Madam, there is not an issue related to the imbalancing or the GradCam. GradCam is a which technique explainable AI that comes after your model got trained. After your model got trained, you apply GradCam to see the images, to see the results. That okay,
But
I have,
the we are showing the result, and then we can prove that it is another 99%.
huh? It
We
is
can
90.
prove, right?
Yes, 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 yes. But the point is, madam, overfitting is a problem in ML
Hmm.
model, and GradCam is explainable AI technique related to how model came to a conclusion that this is a particular category of an image. Now, why overfitting happen? You are asking that imbalancing in the data. Okay, imbalancing in the
Okay.
data. Now, understand, madam, what I'm saying. Okay, you are available with the images. Okay, fine. You apply basic pre-processing over the images, like converting the image into color image, for example, because just X-ray are grayscale images, you convert them into
Yes.
RGB. Okay, this is the basic level
Yes.
pre-processing you apply. You convert the images into 224 or 224. This is what you do, madam.
Yes.
Then,
Yes.
madam, next is you have to normalize each and every pixel value. This is what you need to
Yes.
do. Okay, these
Hmm.
things happen. Now, next comes the augmentation. That's what you are talking about. Okay, that's what
Yes.
you're talking about. So, ma'am, what we do is wait till here. Everything needs to be done on every image. Okay, till here, all
Hmm.
the steps which I mentioned, these three will be done on every image. Next, what you do is you divide your images into training, testing, and validation. Okay, then, madam, what you do, you apply augmentation. Okay.
Yes.
Mostly, madam, if you apply augmentation on training, that is a better idea. Okay, basic augmentation can be applied on testing and validation, also not an issue. You apply more of the augmentation over the training, that is something important. For example, you do rotation, you do horizontal flip, you do vertical flip, you do brightness, you do
Hmm.
contrast over training of the images. Okay, testing
Hmm.
validation, you can go ahead with rotation and translation. That's it. Not that much brightness, contrast. Not so as many as you do the augmentation over the training. That means you are creating diversity in the training data.
Hmm.
Okay, fine. This thing. Also, madam, you have to only balance training data. Only training
Hmm.
data. Don't touch these two.
Yes.
Do not touch.
Even though we done that, the data argumentation,
Hmm.
slightly it is showing as imbalance. If it is some such kind of another situation came,
Huh? Ma'am, I guess
maybe
if you slide imbalance, madam, it will. If how you balance, for example, I do oversampling.
that maxima to minima conversion or something we can do, right?
Oversampling. Ma'am, that means maximum, for example, you are having A, B, C, three classes. A is
Yes.
100, B is
Hmm.
60, C is 40. So we need to make 100 all. So in oversampling, we add 40 here, we add 60 here to make it all 100. Okay, so what we do, we create the duplicates, random duplicates of the existing.
Hmm.
This is oversampling. And undersampling, we reduce the number of images according to the minimum category class. So we have to cut off the images from here also, and we need to make 40, 40, 40. This is undersampling. So
Yes.
if you are having undersampling, we do very less, because the point is, why unnecessary we reduce.
Reduce.
Okay, so there is no sense. Either we do
Hmm.
oversampling.
Yes, yes, yes.
All right, fine. And there is a challenge related to data integrity also. The data should be
Hmm.
consistent. The data should be correct. The data should be valid. There should not be no errors present in the data. That is why we apply pre-processing prior everything. RGB. In fact, madam, if your images are not good in quality, you need to apply CLHAE. Okay, make it good pixel intensity, then color, then transformation. Also, madam, in medical images transformation may affect. We have also seen in the previous research paper, converting an image, transforming an image may affect. This is a medical image.
Hmm. Hmm.
If
That's
you
what.
apply transformation, medical images are affected, because this is body organ, not a normal
Hmm.
image. This is also an issue. But we did experiments in our models. We are getting the scores, okay. But still, there is a scope of research beside, because we never train a model with different image sizes. Okay, we train a model with some particular thing. So apart from that, is there any maths present which don't require such kind of transformation, and we can get the feature? We can make a model. Right now, I'm also working on logic gates. I'm looking forward to work on logic neural network. Okay, I'm currently reading the papers and all. I guess I will be putting that into my research perspective. All right. So there are many things which are happening, and there are question in each and everything. So, madam, if you talk about gradcam and all, first
Hmm.
divide this thing, balance this thing. Okay, balance this thing, then train the model with the training data. There will be no imbalance. Okay, because you already balanced
Yes.
training by oversam. There is no imbalance. After that,
Hmm.
test your model. Whatever with the result you got, fine. Then you need to apply gradcam. Look for gradcam results. That's what you need to do at the end.
Yes. Yes, sir.
Grid camera. Which area is highlighted in the image?
Hmm.
And for that, you need to take the last layer. Let's say convolution layer number 5. Convolution
Hmm.
layer number 5. That is the last layer. So we need to take that.
Yes.
Okay. Fine. This is what happens. All right. So the authors are in depth related to vision transformer. Okay. And I was teaching you the notes. Why radiomics useful? It covers hidden imaging properties, highly interpretable gray level non-uniformity, widely used in oncology, COVID-19 survival analysis. That is why this radiomics, this mathematical representation of pixels or image data is important. Okay. Now, in the paper, the authors use radio mix as an interpretable complement raw pixel vision transformers. They extract radiomic feature from the small patches 30 to 32 of COVID-19 text, and they apply first order GLCM, that means traditional machine learning algorithm or the techniques for feature extraction. Later on, integrated them into a hybrid model. This allows feature group level importance per group attention decomposition in heat map, better clinical explainability. So again, by this research paper, traditional machine learning came into front, and I have already shown you that traditional machine learning techniques are also good ones in giving the accuracy or the scores. Here also they are saying the same thing. Authors, they told that extract radio mix from small patches. Okay, so you are having an image, you divide it into patches P1, P2, P3, P4, P5. Apply radio mix over the patches. Let's say patch is 32 cross 32. Radio mix means you need to apply GLCM. You need to apply CLHAE. You need to apply this, etc., etc. Whatever the traditional ML algorithms are, you need to apply over them to find the relationship between the pixels. Not relation, statistical relationship. That's what I can say. Statistics, distribution of pixels. That's what I can say. To find that, okay, find that, and make a hybrid model, combining them, integrate them into a hybrid model. So you do the feature extraction by traditional techniques and combine them. Okay, advantage. Clinically meaningful. No need for massive labeled data. Complement deep learning. Limitation is sensitive to image quality. Okay, so depends upon the image. This part is sensitive. Anyways, authors told that we can perform this activity. Contrastive alignment. Okay. Contrastive alignment, also called as contrastive modality alignment, is a technique from self-supervised. Okay, self-see, learning from self. We have seen in previous sessions. Self-supervised and multimodal learning aligns representation of different modalities into the shared embedding space. So I guess we did one research paper also, and currently too we are in a competition to get it published clip. Okay, so like multimodal, that's what they are saying. Multimodal means a model which is trained on text also, images also. Okay, so we do have such kind of models where text and images both are taken, and huge model. For example, medically, for medical we are having bioclip, like something model. Okay, so what they are saying, it is a technique from self-supervised and multimodal learning that aligns representation from different modalities into shared embedding space. So you know what happens here, what they're trying to say. They are saying that self-supervised, self-learning. They're talking about self-learning. You know, we do prepare a model. Okay, we give images to the model, train the model. Now, for example, some new image came, new data came. Are you looking forward to retrain the model? No, sir, this is a hectic process. So, right now, we do have self supervised learning. If anything new comes to the model, model will learn itself what actually it is. What actually it is. That is self supervision. I try to analyze its representations. And if it's something new, it push those representations into embedding space. That's what they are saying. For making them learned by the model. Check what they are saying. They are saying it is a technique from self-supervised and multimodal, because this is multimodal contrastal, or it's multimodal. That means text and images both are taken to train a model. It's a huge model. So it learns from multimodal that aligns representations from different modalities. Different modality means text and image. We have combined the text and images. We do have the encoder, text encoder also, image encoder also. We took both of them and we trained those encoders to make a huge model called as clip. Okay, different modalities, different views on the same data. Text for that written, images for images also given for that, and into shared embedding space. That means text and image both are in a same embedding space only. They are in a same embedding space. That means they are converted into vectors, but they are present in the same space. Okay, that means convert text into number, convert image into number, put both of them into, because both are numbers, put them both into embedding space where we can represent vectors by them. So make embeddings of semantically related items, positive pairs close together. which pushing unrelated data into the latent space. So, if there is something new, it will not match with the existing. That will be pushed into the latent representation. That means far away from the one which we have learned. This is what happens in contrast to learning. And it's not new thing. We already learned in the previous workshop. You seen this thing in the previous workshop. Contrast to learning, contrast to alignment. Those who are same, their embeddings will be same, their vector will be same, they will be close. Those who are not same, they will be far. It is contrastive alignment. So it uses contrastive laws. Okay, that means normalized temperature, scale, cross, entropy laws. Mathematical way, we can write it like this: LCL minus 1 by n log exponential similarity by tau exponential similarity by tau. So this is image. Okay, we are having image. Okay, Zn, that will be the vector. This is similarity, that's a cosine similarity. Positive pair, the matching will be happening between the pairs. Negative, there is mismatch. Tau temperature is diversity, control the sharpness in the distribution. So this will be randomness for any random data. Okay, any random embedding we are taking, we are having image and we are matching them. If they match, then okay. Not match, then there's a negative pair. They are matching, then they are positive pair. Not matching, that means negative pair. Temperature is to control the sharpness in the distribution. This is clip. This is clip. Contrastive language image pre-training or SIM CLR. We have used in our research paper also. Currently also. I'm making one paper in which I'm using this clip. Alright. Fine. So in this paper, we are having contrastive alignment also. Like the pixel branch, pre-trained VIT on image patches, TLS token, and radiomics branch, feature grouped and pre-processed produce two latent representation for the same chest X-ray images. Okay, so we are having a pixel branch. That means pre-trained VIT on images to CLS token, classification token, and radiomics branch also is there. Features grouped and pre-processed. So we are having image, we give it to the VIT branch, we give it to the radiomics branch. From radiomics, we are collecting the traditional machine learning feature extraction technique, which are grouped together, and from here we are taking latest vision transformer techniques. Okay, two representations are created for the same chest X-ray. So this is representation number one. This is representation number two. One we are creating with the vision transformer, or one we are creating with traditional machine learning algorithm. Okay, we do have also Cox survival loss. That is L total equal to 1 minus lambda loss, L Cox plus L lambda loss into LCL. This encourages pixel-based radiomics-based embedding to be aligned consistent to the shared space. So it's a new kind of a loss which has been introduced to encourage pixel-based and radiomics. This is pixel-based. This is radiomics-based. Embeddings should be aligned, consistent with each other. Okay. Some benefits: faster convergence, better integration, different modalities, preserve the strength of VIT vision transformer. So right now we are not only interested in vision transformer, we are taking vision transformer along with the traditional machine learning technique, statistical based. Okay, two branches we have made. One branch is for vision transformer, one branch we have made for traditional technique. Okay, so advantage of contrastive alignment is self-supervised, improve multimodal vision as model to learn semantically meaningful representations. Okay. So these things happen. Here is a paper. Here is a paper. Okay. Fundamentals of the paper. Let me read it. Survival analysis means predict time to event outcome until death, ICU admission, while handling censoring patients who haven't experienced the event by study end. The standard model is Cox proportional hazard model, which estimate a hazard function in the baseline hazard. X are covariates, beta are coefficient. It assumes proportional hazard, the effect of covariates in constant over time. Okay, now authors told that we want to add survival also. We need to add survival analysis also to predict when a certain event can occur, what could be the outcome, or time until death, or ICU admission, like these things. So they mentioned a standard model called as Cox proportional hazard, which estimate hazard function. So there is a function that this kind of bad thing can happen in so and so amount of time. There's a bad thing which can happen in this amount of time. T is a time, lambda t, this is the parameter they are taken. Lambda t equal to lambda naught t into exponential beta k power t into x. So lambda naught t is the baseline hazard, and x is the input, beta is the coefficient. Okay, so over a period of time what bad can happen? This is survival analysis the author mentioned. Like extension include neural network version, etc, etc. Okay, 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 fine. Fine. There are some index values like measure how well the model risk scores the pair of patient. Like higher is better, zero point 0.5 random, one is perfect. And vision transformer you are well aware of, so I think there is no issue of reading about the vision transformer. Radiomics you very well know. I already explained you this thing. Okay. So authors used simplified shallow 1 to VIT model, not the deep model, shallow VIT. Authors use simplified shallow VIT model to study how attention works when we apply Cox. This enabled direct analysis of token level dynamics inspired by the theoretical work of shallow VIT for classification. How? What they are doing? How they are trying to manage? Each image is divided into token. Okay, yes sir, we know. We know. Xn belongs to a real number d into L. L is the token per patch, d is the vector embedding. The output risk is given by this formula. Okay, fxn, if you put this, so what we are doing, each image is a token matrix. And what they are saying, tokens per patches. How many tokens we can make per patch? I think they are going beyond the patch thing. Token per patches, pixel level, maybe like this, image to patch, patch to token. So how many tokens can be there per patch, per patches? And they are trying to identify the risk per each image. That means in that particular matrix they're trying to identify the risk given by 1 upon Sn summation of Al transpose ReLU activation function W0, that is a weight, ASL xn WV xns. Okay. The formula, Sn is the set of active tokens after pruning. So they perform pruning of the tokens. There's a pruning of the tokens. So this is the tokens which are left after pruning. ASL are attention coefficients. Okay. These are attention value. Okay. Given by this formula. WQXNL का ट्रांसपोज WKXNS समीशन, क्योंकि what it is we study ना e की power x. Okay, this is what we study ना, e की power x upon summation of e की power x. Same thing is happening here. But what they are writing, e की power WQX का ट्रांसपोज WKXNS. That means query key. Okay, where WQ, WK, WV, W are the projection metrics, matrices, and AL are token specific linear weights. So they are applying in attention dynamics, telling that we need to study how attention works under Cox supervision. And the formula which they are giving, that make a token matrix. Let's say in an image there are n number of tokens. N is a token matrix. Each image has having n tokens, which are active. Only consider active tokens, not passive tokens or eliminated tokens. So we are having image to patch to tokens, and only consider active tokens and find the risk. This is how we need to find 1 upon number of active tokens, that is set of active tokens, summation, attention scores. This is attention score, this is ReLU, again attention. Okay. Then they are saying this will let us know feature selection and token coefficient. That means which tokens are important. This will help us know. Then training with Cox partial likelihood. Negative log partial likelihood minus f of xi minus log of e की power f of xj. Where where delta I is the event indicator. This is event indicator, and RTI is the risk set time, risking. Now the questions in our mind are sir, we do have two levels, like two path has been made. One path is related to traditional ML, where we are applying GLCM, etc., etc. So many of them are we are combining. At one end, we are applying vision transformer that is shallow in nature. That means we are just picking one or two layers of the transformer. That's what we are only taking. And here also we are identifying the risk. And how we are doing? The author told that wait, you are having image, na? You do into patches na? Okay, okay. No, no, not patches. Token per patches. So just we are looking forward to select important tokens from these patches. So they are going beyond the tokens, beyond the patches. Sorry, they are applying some formula f of xn. That is the formula they are applying. This is risk factor. Risk factor. Because why they are doing, they are trying to identify the interpretability of the attention, whether this attention is giving any risk factor or not. What does attention mean? Attention means to focus. So why we are focusing, boss? Why? What is the reason to focus? Is there any risk factor given to us or not? That is the author thinking. That is why they told that this is the risk score 1 upon Sn. 1 upon Sn. That means take the active tokens, not the passive active tokens. Now, set of active tokens. Then AL, again some attention, then apply a ReLU activation function, and here you need to again summation of ASL, take the attention and the weight multiplied for the active tokens and all. This is the formula. Here I am going to get the risk score. That's what authors told in the formula. Okay, very good understanding of the author. They are in detail. Okay, they are in a detail, and then they applied some Cox partial likelihood of training. That's what they have applied. Okay, and in their experimentation, they are telling that we generated synthetic tokens, and this is the value of lambda we have applied. Okay, done some simulations. Okay, so with simple or standard vision transformer, and why applying radiomics, and the hybrid transformer with the radiomics, okay, we are getting such risk thing. Okay, per patch radiomics feature grouped with 12 classes of VIT attention heads treated as additional token, shallow transformer taken, and then here is the risk which they have calculated. These are the formulas they have applied. Contrastive alignment also been taken, inspired from CLIP, to identify which are similar, which are dissimilar. That means positive and negative. Okay, and then they have also applied this Cox loss. The data set which they have taken is COVID-19 CXR data set. Five-fold experimentation they have done. Okay, and hybrid VIT they are getting 99.2% faster convergence they are getting. With only radiomics 70%, because radiomics is not capable. With the vision transformer they are getting 74 to 75 something, but with hybrid VIT and mix up with the radiomics, I guess they are getting 99. Okay, so faster convergence with the radiomics, this hybrid model with they have preferred. Okay, so pixel VITs focus on lung field, clinically sensible, etc. etc. Radiomics decomposes classification attentions, example GLCM, etc. etc. Feature importance has been calculated. Advantages, this is interpretable in nature, performance, flexible, theoretical grounding, etc. All good. The only thing is you are taking a shallow vision transformer. You are taking radiomics. Okay, small in risk. Hybrid helps more. With only radiomics will not going to do anything for you. You need to combine. Single COVID-19 cohort, 20 EPOs, potential overfitting. Okay, stop. Early stopping is suggested. Deep VID, slow EPO, radiomics only, and these are some issues with which they have mentioned. Okay, but I like the approach of them. They done token pruning, multimodal fusion, feature grouping, okay, optimization, visualization. Okay, that's what they have done. So application is not only related to just X-ray. The application is also related to other medical image data also. All right. So I guess they do have something in their mind, like image. One is given to radiomics, one is given to shallow VIT. They had novelty in attention. Novelty in attention. Actually, they focus upon survival rate in attention by Cox interpretation. That is what they did. So we are getting from radiomics, we are getting the result from VIT. So this is what we are mixing. We are training our model, and we are now getting some good score rather than taking individual. If this is individual fail, this is also individual not going to be much more justified. But when we are combining these two and calculating combined loss, like contrastive learning, okay, they have given the formula positive pair and negative pair. They have given the formula. According to that, if there is a training going on, loss has been calculated. Okay, we are in a better position. Okay, fine. So what we can what we can grasp, the context of the paper, the importance in the paper is the attention. Okay, pixel level. token level token level classification. Okay, which token is important, which token is not important. So far in Vision Transformer, we do patching and then we do embedding and we train using attention. Now, what they are saying, no, 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 not patching. I'm talking about token. So we will be having number of tokens per patches. So we need to define tokens, not patches. And then you need to apply attention, token based. Find the survival rate. Formula is there. Find the survival rate. And then calculate the loss by considering this also, this one traditional ML and the one which you got at the moment, by applying the survival rate classification based shallow vision transformer outcome. Combine them, train your model. This is the theme of the paper. They tested over COVID-19 images, CXR images. Okay, and they told that we are, if we take individual radiomics, not good score. If we take only VIT, not good score. But we combine this hybrid both VIT and the radiomics and apply this. Okay, like shallow VIT with the risk survival risk factor included in the attention, token pruning if we apply, and we introduce a new loss formula related to contrastive learning where we have positive and negative thing. We got some better result. Good paper. Good paper. Next time, I guess I will take this again as an inspiration for making my paper because they have introduced survival rate. They have introduced about Cox. I'm looking forward. What is the alternative of Cox? To see what is the alternative of Cox. How we can change this formula. They told it's generalizable. Quickly, it converge and give the result. We'll see. Okay. Code interpretation. We'll do ahead. Okay, not today. We'll do ahead. I will again call you. Again, we'll take a meeting, discuss the results related to the chest X-ray, what we have done here. Okay, and see the outcomes. However, my concern today was to introduce you the paper to talk about the concept which is used in the paper. It was a vision transformer, but as we have seen, not the only concept of vision transformer has been used. They have applied more than the vision transformer. Okay, here is the maths which they have applied apart from the transformer, because this attention is very well known to you. I'm not talking about this attention mechanism already. Apart from the attention mechanism, what the authors told that motivated by the development, we examine how attention behaves under survival supervision. Simplified transformer setting. Now we are talking about survival. Adopting shallow architecture based upon the previous work. Based upon the previous work, we introduced that, let us say the observations are x1 to xn. L tokens are there. In an image, we divide the image into tokens. Each token represented with a D dimension. L is the number of tokens, D is the dimension of the token. Okay, from the image patch. So collect the tokens from patches. So far, we are only restricted to patches. सर पैच है सर पैच का एम्बेडिंग कर दो सर अभी अभी नो नो नॉट लाइक दैट वी आर अवेलेबल विद द पैच डिवाइड द पैच इनटू टोकन पैच की एम्बेडिंग करो टोकन की करो सॉरी okay and then subset of active tokens after sparsification we need to find the active tokens and then apply this formula. This is the risk factor, this is the risk formula, and then this is the attention formula. That's the game which authors did, and everything is mentioned what it means, what xn xnl xn wq, these are the weight. Okay, this is the linear weight, this is attention. Okay, attention coefficient, all these things are mentioned in the research paper, you can read. This is a detailed paper. All right, fine. So, like their experimentation also mentioned in the research paper. They worked on synthetic data also, something that's what they're saying. Synthetic data model performance. All right, that's their findings. Synthetic data for true level relevant token recovery. So they did on some synthetic data. Then the survival outcomes for COVID-19 chest X-ray they applied. Okay, fine. Here are the same formulas which we have seen above. Here is a loss formula which we have seen above in my nodes. Here is the entire architecture. So we do pixel level embedding. That means divide the image into patch, divide the patch into token. That's what they are calling as pixel level. And then give it to the transformer encoder image. Okay, transformer encoder to image classification token. This is the classification token which we are going to achieve after applying this to the encoder. And then contrastive loss, that means contrastive loss means positive and negative alignment. Separately, we are getting a radio mix. So we are adding a radio mix and image level classification to find the loss. This is what happening. So at one end we are pushing the pixel, one end we are pushing the radio mix. Then loss will be calculated combined. This is the final architecture, proposed model architecture. And it's not like sir something which we cannot we did made. This is not. I also made one paper in which I took a traditional machine learning and I took pre-trained model like VGG16. I applied this one also, applied this one also, and combined the result and train. I did that. It's a hybrid model. They are also making, but the thing which they change is this survival. I haven't know about the survival thing. It's new for me. Else, we combined CNN also and Vision Transformer also. Right now, these guys are working on pixel token level. I worked on patch level. Okay, one more thing came into the learning perspective. It's a hybrid model. We also made a hybrid. Anyways, that's the thing which I want to teach today for today's session. All right, got it. So I'll share you the notes which I made. Okay, paper I already did. You can check it. Code I will share. We'll discuss over the code also. This is a good research paper. Something new we have learned over the vision transform. We'll continue. All right, fine. That's what I need to talk for today's class. I don't want to give you something overburden. Okay.